There are about as many methods for reviving old lead-acid batteries as there are battery revivers out there in the world. And the topic of battery desulfators, a kind of electronic device designed to bring life back into old dead lead acids, is a very controversial topic to say the least. There are many designs available on the internet, and there are even more videos and advertisements claiming to provide devices which will revive your lead-acid batteries, but they often don't provide any proper schematics, and the ones that do often tend to be of not very competent design. One of the most common ones floating around out there is something which looks kind of like a switching regulator, but it actually doesn't do anything at all. If you have enough creepage inductance in your wiring, then maybe it can produce some kind of high frequency noise, but it's really nothing worthwhile. So I decided to try and do something about the controversy. What you're looking at is 14 batteries which have been connected in a large battery pack out of a UPS, which was scrapped when its internal battery failed. And these batteries have just been sitting on a shelf for probably a few years, and they have simply self-discharged into oblivion. They all have between 5 and 1 volt in them, and they obviously don't work very well as it is right now. So I figured I would try and do some kind of scientific experiment to determine whether or not any kind of desulfation device might actually have any merit to it. What you're looking at there is a desulfation device which I designed myself about a year back. It's in essence a microcontroller programmed to act as a switching regulator, on which I've basically omitted the output filter. The only filtering on the output is a half-ohm resistor, in order to limit the current, in order not to make the output transistor explode. And what this thing is capable of doing, and as you are seeing on the scope, is producing current pulses at a frequency of about 30 kHz, and it can produce about 5 amps of peak current into a battery. And the way it works is by just pulsing a current through a coil and then letting that coil discharge into the battery without filtering. So the voltage will rise across the battery terminals until such time that the battery starts conducting, i.e. accepting some kind of charge or just shorting out. It's programmed in such a way that it actually has a feedback network inside it, which will roughly regulate the voltage of the battery to 13.6 volts, while ignoring the pulses that has a low-pass filter on it. So the DC voltage of the battery will be about between 13.3 and 13.7 volts depending on conditions, while the pulses can rise up to 5 to 10 volts above that when it's discharging the coil into the battery. The point of this is to allow the battery to absorb current at a high voltage without having to put a high DC voltage constantly across the battery, which as I'm sure a lot of you know, will cause the battery to expel its electrolyte in a rather violent manner, causing the battery to fail absolutely and without discourse. So in order to test this device, I have grouped these batteries into groups of 2, based on their open circuit voltage at the time of delivery. At the far left you have group number 1, which had an open circuit voltage of about 5 volts, they're labelled 4.88 and 4.84. And over there in the back you have group 7, which had a voltage of about 0.8 and 1.3 volts. So they're grouped according to the rough condition of the cells based upon nothing but that. I'm going to subject one of the batteries in each group to the desulfation device, and the other to a more traditional way of reconditioning a battery, which is to just apply a rather high charge voltage over a long period of time. It's usually starting out at something around 30 volts, and once it starts conducting a bit you lower it down to about 15 or 14.4 or so, a more sane charging voltage. Doing that is a relatively tried and true method of getting some life into a battery, because one of these batteries, when they have really been sitting for a long time, they have been discharged, just putting a normal charger of about 13 to 14.5 volts across them will simply not have enough voltage to make the bad cells conduct electricity, so the battery will just sit there indefinitely and never begin accepting charge. A lot of the kind of phony desulfators you're going to find will be a device which connects to the electrical grid and basically just capacitively current limits it and put it through a diode into your battery, putting a very high AC voltage across it, which very violently can kick the battery back into life, but it can be quite dangerous, to say the least, and I don't really approve of that method. The method I'm going to be using is to just hook my laboratory power supply up to it and manually adjust the proper DC voltage. The way I'm going to perform this test is to connect these batteries to the device and a charger and let them sit until such time that they stop drawing a current when switched to a float charge voltage of, let's say, 13.6 volts. A battery of this size should be drawing about 10 milliamps or so at such a float charge voltage. If they never reach that stage, I'm going to limit the time they spend connected to the device and charger to 1 week at a time. Once that has happened, I'm going to do a discharge test at 1 amp using my computer-controlled constant current sink, and we will see how much capacity is in these batteries. I'm going to repeat this process a couple of times in order to see how the batteries respond. I'm not entirely certain of my methodology as of yet. That's going to have to be derived from how the first group actually behaves. It might take 1 or 2 cycles of the batteries in order to properly make them wake up, so to speak. We're going to have to see about that later in the video, but for the time being I'm just going to hook these batteries up, starting with group number 1 over there to the left, and let them soak for a maximum of 1 week. The batteries in question are NS's data-safe batteries, which are relatively high-grade sealed AGM batteries, which are specified to be 5 amp hours at a 20-hour rate, or at 1 amp they should last between 30 and 40 minutes when new. I don't think we're ever going to reach anything like these specifications ever again, but it is a baseline which we can work from. These batteries are specified for a standby life of 3 to 5 years, and this unit they came out of was made in 2008. I was informed it had been sitting unused for about a year or so. I can imagine it being slightly more than that given their very low state of charge. So these were, even when they were taken out of service, at the end of their life. So we really can't expect a perfect performance out of them. However, since they did get taken out of service due to another pack in the system failing, these should not be lacking in electrolyte and so forth. They have not failed due to overcharging. They have failed due to sitting unused for a prolonged period of time, which makes them excellent subject for this video, since a lot of batteries you find in used UPSs are going to be swollen, horrible and overheated, and that doesn't seem to be the case with these. And for those out there who aren't giant battery nerds, here's a rundown of a few charging and revival methods. So when you're dealing with lead-acid batteries, this is what a normal so-called three-stage charge is going to look like. It's going to charge at a constant current for some amount of time until a set voltage point is reached, at which point the current is going to start tapering off as the charge enters a constant voltage mode, and after the current has dropped to a certain set value, it's going to lower the voltage and enter a lower voltage float charge mode, where there will just be a very small quiescent current running through the battery. Now, if you have a bad or worn out battery that's been sitting for some time or is old and worn, then you're going to find that instead of the voltage of the charger being low at the start, it's going to jump right up to the constant bulk voltage setting, and there's going to be almost no current flowing through the battery. However, after some time of this, the voltage across the battery terminals is going to drop and the current is going to increase until it then performs a normal charge cycle like any other battery. If you however have a really bad battery, as this we are about to do some experiments on in this video, the charger would simply sit flatlined at its constant voltage setting and the current would never ever increase. When you disconnect the charger from such a battery, the voltage would probably sit at around 12 volts for a while and then drop back to almost nothing. One method for getting a battery out of this stagnant state is to provide it with a very high terminal voltage, usually of the order of between 20 and 50 volts for a 12 volt battery, which will just force more current to flow through the battery as per Ohm's law, and this might sometimes cause the battery to slowly start accepting more current until it finally, after any amount of time, enters a normal charge cycle. However, while you are applying a hugely large voltage across the battery, it is going to wish to emit a lot of gas, turning its electrolyte into something to be whisked away with a breath. So you really want to spend as little time as possible in this high voltage area. But you really can't avoid doing that, since you need the high voltage in order to push the current in order to make the battery accept a charge. So this method really has some very bad compromises, and it usually leaves you with a very mediocre battery. Now, the pulse method, or the desulfator method, as I've implemented it in this application, has a voltage-controlled PWM controller, which will shoot high current pulses through the battery. Since it operates on a feedback mechanism, it's going to have a very low duty cycle while the battery voltage is high, not allowing there to be any severe amount of energy produced in the battery, which would allow it to produce gas. And this is usually going to cause the battery to still kind of wake up and start accepting more current, at which stage the voltage will very rapidly drop due to the very small amount of energy contained in the pulses being fed to the battery. Once the battery has reached a set voltage point, the controller will start raising the duty cycle and increase the amount of energy contained in the pulses. The dotted line in this graph represents the pulse duty cycle, and by proxy the current running through the battery. And it will keep adjusting the duty cycle in order to keep the battery at a constant voltage. Now, this will also cause the peak voltage across the battery to remain quite high. It can be several volts higher than the real RMS voltage of the battery. But this peak voltage is going to decrease as the battery becomes more and more alive, until such a point that the battery basically enters a normal charge cycle. However, it is going to still operate in the pulse PWM switch mode converter mode, so it's going to be usually something like a bit of an oddball charging curve. It isn't going to be as straight and rock solid as it usually is, but this is basically a normal charging curve, and once the set voltage has been reached, and the controller has spent some time in its maximum duty cycle mode, where it's just pulsing as hard as it can, the battery will reach a set voltage and it will basically be done. It will have accepted about as much charge as it's going to. At this stage, the controller is going to enter minimum duty cycle mode again, and there will be a rising peak voltage over the battery. And at this stage you should just disconnect the desulfator and do a cycle on the battery to see if it's worked, because at this stage you are just trying to push more energy into a fully charged battery. So the obvious advantage of a system like this is that you spend a lot less time in the dangerous guessing zone, and you are also able to push energy into the sulfated part of a battery, which are very reluctant to accepting any kind of chemical reaction, while keeping the mean voltage of a battery relatively low. In fact, my device keeps it at a normal float charge voltage. So you really should, in theory, my very flawed theory, be getting about as much energy into the battery as is possible without boiling away all the electrolytes. So that's the theory. Now we've just got to wait a few weeks and see if it applies to practice. Alright, so let's enable group 1. So as the setup is, we've got this battery labelled P connected to the desulfator device, and this one labelled V is going to be fed a 25 volts DC voltage limited to 100 milliamps, and that's going to be the setup for all the batteries, unless it proves to be vastly insufficient in this first test. So let's see what happens. On the scope we are monitoring the terminal voltage of the pulse battery, which at the moment is about 4.4 volts. The terminal voltage of the pulse battery right away rose to about 17 volts, and we have roughly 2 volts of ripple across the terminals. And if we measure the output current shunt resistor, we will notice that there is very little in the way of current entering the battery, with a peak voltage drop of about 100 millivolts, giving about 200 milliamps of current flow. And if we probe the gate pin of the switching transistor, we will find that the device is stuck at its lowest duty cycle of about 3%. This is due to the high terminal voltage of the battery, which is going to drop, and the duty cycle is going to increase with time. As for the pure voltage battery, it is consuming about 10 milliamps at 25 volts, and that current is also likely to increase over time, and perhaps it might even trigger the current limit and allow the voltage to drop. But that's going to take quite some time, and we'll have to check back on it later. However, just a few minutes into the test, we can already see that the terminal voltage of the pulse battery is actually starting to drop, which means that the ESR of the battery is decreasing and it's becoming more and more capable of accepting a charge. About 15 to 20 hours into the test, this is what the score is. The voltage battery to the right, which started out at 25 volts, has, during the course of these hours, drastically lowered its internal resistance, and it started to consume quite a bit of current, hitting the 100 milliamp current limit I set on the power supply. The pulse mode battery, the desulfator battery, has not done a whole lot, although it has started to consume some current rather than the basically none it started out at. We can get a better idea of what it's doing by having a look at the oscilloscope. We are now probing across the battery terminals right at them, so this is the exact voltage of the battery itself. And we are DC coupled, and we are having an average voltage of about 13.7 volts, but we are having a maximum voltage of almost 30 volts up here at the peaks where the coil is discharging into the battery. And this waveform is looking quite ideal for what you would wish to see out of one of these devices. Because if we zoom into the waveform, we can see that we don't really have any high frequency ringing, which would indicate that we've just got a hugely high internal resistance on the battery, but rather we have a nice, smoothly rising and then quickly and slowly dropping waveform going, which means that the battery is in some way allowing current to pass through it rather than just allowing it to ring for a while and dissipate in all the stray capacitance and inductance in the circuit. You can also see how the device has entered its constant voltage mode, where it's varying the duty cycle of the transistor charging the coil by watching how the peak voltage of a waveform is kind of jumping up and down. That is 1 PWM step going back and forth. And the longer this battery keeps going and the better shape it's going to end up in, the duty cycle is going to increase, despite this hump decreasing as the internal resistance of the battery improves. Okay, some time has now passed, and we've come to the stage where it's time to test the first battery. So here's what we're going to do. This is the first group voltage battery, which seems to have satisfied the conditions I set for being charged. So it is right now connected to channel 3 of my current sink there, and at the moment it's not doing anything, but it's just connected on to my old laboratory supply there, which is set to charge it up at 14.4 volts at 1 amp once it finishes loading. And here's the UI for the current sink. As you can see, the battery is currently at a voltage of about 14 volts, and we are about to start a test at 1 amp, which is going to terminate at 10.8 volts. So, let's see what it does. Nothing. Let's try again at 500 milliamps. That seems to be a bit more doable, but this battery certainly doesn't seem to be a capacity king. So, I'll just let it run. It's going to run for about a minute at the most, probably, and then I'll note the results.